from the chapter. So let's go one by one. Okay. First, ping of death. The ping of death. Okay. A lot of the vulnerabilities that we see at the OSI layers, right, or the TCP/IP layers, is the faulty implementation of the protocol. So, let's say, for example, if you wanted to write an OSI implementation of the FTP, right? So what you would do then is you would go to the guidelines, you know, what the FTP is supposed to do. So you say something like, you know, FTP, RFC, okay, and they'll tell you which RFC talks about the FTP protocol. So there it is. So you'll have that. And then if you're, you know, all the requirements of what the FTP server is supposed to do is here. It's all here. Okay, so then you have to implement that, don't you? Right? So the implementation is really, you know, how you program this thing to make sure that all these things happen. Okay, and nowhere in this FTP does it say for you to encrypt the username and password. That's why it's not there. Okay, because if you add that, it wouldn't be an FTP, would it? It would be, you know, SFTP or FTPS. Well, actually, let's so. The SFTP, okay, is a secure shell file transfer protocol. So it is basically an FTP tunneled over SSH. Okay, that's what an SFTP is, right? The FTPS, right, is a extension to the FTP. So here it is. FTPS is an extension, or FTP over the SSL. Extension of the commonly used file transfer protocol adds a support for TLS. Okay, so now you know the difference between FTP and FTPS and SFTP, right? And so as I mentioned, getting back to my initial point, is that how you implement this thing that's usually where faultiness lies. Okay, so then the ping of death is about the, not ping, so which is ICMP. So if you look at ICMP, okay, RFC, so here is the RFC 792, and here's about the Internet Control Message Protocol. Okay, and if you look at Echo, okay, so if you look at Echo, so this is it right here, right? And it's the echo or echo reply message. And notice how simple it is, right? And yes, it does have data, but it doesn't expect much of the data because you're just looking for the type. So the type will be here. See right there? Okay, that's what you're looking for. And if the type field is 8, it is the echo message, 0, echo reply message. Right? That's all there is. And nowhere in there does it say you use this thing to send data. It doesn't. Okay? So ICMP is supposed to be very light, very small, just do its job, right? For just indicating certain things by using these flags. Well, here's the problem then. Ping of death is where somebody actually puts a huge amount of data in a payload. There is a data field, but it doesn't expect it to be any size at all, but in the ping of death, they put a huge one. So what is the problem if somebody were to just put that in there? Well, the problem is the implementation. So if the implementation checks and makes sure that, if they are to look at data, that they make sure that they check the data to make sure that it does not break their application if they were to consume it. Right? If the program were to use it, make sure it doesn't break the program. But some programs don't. And the reason why some implementation of ICMP does not check for the payload is because it's not in the RFC. Or, it's not supposed to be, right? So you're not supposed to use ICMP that way, but people who break protocols do those things all the time. So ping of death works if the implementation is not checking for the payload, and if the payload is huge, it eats it up and it gulps on it, right? It's like it hiccups on it, and then it could bring down the network. It could just break the application. Okay, so that's basically what a ping of death is. But the common fault is the implementation fault. Okay, So it's a logical flaw. Any questions on ping of death? No? Okay. All right. So that's the one. The ICMP redirect attack. Okay. So let's take a look at ICMP redirect. Okay. So the ICMP redirect happens. Let me just go ahead and go into the whiteboard for a moment. Okay. So what happens here is we're talking about redundancies. Okay. And I think we talked about the single points of failure in the design. So in order for it not to fall in, to fall off, when something goes wrong, people can have two default gateways into the network. Okay, somehow, in a switch somewhere. Okay, and then you have all the hosts kind of connected. Okay, and these two routers, right, have two different IP addresses, obviously. Okay, so the default gateway would be, let's say this one is R1 and R2. Okay, and when you set up a PC, you set up several things, don't you? So you set up the IP address, right, subnet mask, right? You set up a default gateway. That means you take that IP address and you stick it in here, right? And then maybe you have a DNS. So there's nowhere in the client setup where you could put two default gateways, right? You just put one default gateway. So if you had R1 as a default gateway, and if this thing goes down, how is this going to know that it's supposed to actually go to R2? And the quick answer is it doesn't, right? So it'll try to keep on sending to R1, and R1 is down, so it won't be able to get through. And that is going to be a pain, wouldn't it? Okay. So there are several ways to create router redundancies, such as sharing a virtual IP. So you have the R1, so IP for R1 and IP for R2, and these two are always checking to make sure who's up and who's down, and then they actually share like R3 IP for R3, which is a virtual IP. Okay, and so the default gateway is set to R3, and the actual servers, actual routers R1 and R2, only one of which answers to that virtual IP address. That's the one way of doing it, but there's another way of doing it, and which is called the ICMP redirect. Okay? So the ICMP redirect is when the R1 goes down, R2 sends an ICMP message, said, look, you don't send it to R1, send it to me. Okay? Remember, ICMP is a troubleshooting feature. Okay, so that's basically what this is what they do, right? So it's to allow for the redundancies to happen. But what if you have a hacker in the midst? Okay, so there's a hacker, okay? And let's say there's nothing wrong with R1. Let's say there's nothing wrong with it. Okay, let's say there's nothing wrong with it. But this person sends an ICMP redirect. Oh, sorry. I moved this body. There we go. Let's say this person sends a ICMP redirect message. It says, hey, ICMP redirect, I'm the router. Okay, so now these folks will start sending the traffic to this person, thinking that it is a router, and then this person can go ahead and send it off to the proper router. So now you have a man in the middle, don't you? You have a man in the middle. Okay? And let me just go ahead and show you the write-up on that. So it's the ICMP type 5. So it's type 5. So here it says the ICMP redirect message is used to notify the remote host to send the data packet on the alternative route. A host should not send an ICMP redirect message. Redirect should only be sent by the gateways, right? It says it should not, right? So once again, there's got to be a vulnerability. The vulnerability is that in the case that I just explained, it was the host who sent an ICMP redirect. It was not really a router. Okay. And if there's anything else, so these things are stated in the RFC. Okay. And the problem, of course, is that as you could see, RFC 1349, RFC 816, RFC 791. My goodness, the redirect stuff is like all over the place. So no wonder it's very hard to implement these things right? Because whoever's reading it has to implement it based on all these RFCs. Okay, so there you go. Oh, I think this is a pretty good book. And this is all the RFCs about the ICMP redirect. Yeah, pretty hard. Okay, so any questions on the ICMP redirect? Okay. Okay then. We shall go to the next one. Traceroute exploitation. Traceroute exploitation. So we saw traceroute, and we talked about what can a hacker do, right? So traceroute itself is not an attack, but it is a way for the hacker to figure out the environment so that they can plan out a very coordinated, very strategic attack. That's basically what a traceroute is for. Okay. Let me go ahead and combine the traceroute thing, okay, another way of thinking about it, with the, let me see, spoofing. Okay, with spoofing. So spoofing is where you have, so we'll do a blind spoofing. Okay, so in the effort of doing the blind spoofing, I will also explain another aspect of the traceroute exploitation. Right. All right. So let me go ahead and go to my whiteboard. Do a whiteboard. Everything's good. Save. So let's go ahead and take a look at the environment. Let's say you have firewall. Let's say you have two people with their workstations. Okay. And on the internet you have an attacker. Okay, so the attacker, here's the target. This is the target. Okay, and this attack launches. Let's say if somehow they launch an attack through the firewall, right there. I mean, this may not happen, but I'm just saying, right? Let's just say this happens, and the IP address is spoofed. So the source IP is set to, let's say here's a spoofer. So let's say this is another victim. Okay, so the source IP address is set to the victim's IP address, and obviously the destination is set to the target. Okay. Now, let's say this is an attack, okay, and the target sees the source IP of the victim. So it may go ahead and reply back to the victim. You know what I mean? Or and this may say, "What are you talking about?" type of stuff, right? This may happen. Okay. So whatever happens, because the IP address is set to the victim, right? So whatever happens here, whether it blows up or whether it doesn't, the attacker can't see it because it doesn't come back. The replies, they do not come back. Okay. So this is a case of blind spoofing. That is, you're blind to it. You kind of throw the bomb out there, and you can't see if it did anything or not because it's on the other side of the wall or something. Okay, so this is basically blind spoofing. Okay, so then how would the traceroute thing come into play? Well, before we do the traceroute, okay, how can this person say, you know that attack that I just got? I think it's a spoofing attack. Okay, so how would this person know that this was initial attack that came through was spoof? Well, a couple things. Remember the TTL, time to live? Okay, so if the target was looking for TTLs, or maybe after the fact they were actually looking for TTLs, just analyzing what happened. And if you have an IDS or something, maybe you have log of all these traffic, and then you just notice the TTL. Let's say that this person set the TTL, initial TTL, to something like, let's say 30. Okay, but in fact, let me actually check that. Default TTL. I'm just seeing if there's actually a default TTL on anything. Okay. Oh, the default TTL values. Yep, there it is. Oh, it's another RFC. Oh, okay. So current recommended default time to live for the Internet Protocol is 64. Wow. Okay, so that's interesting. Let's see. So it's 64. So let's say everybody plays by the rules and they put 64 in. Okay. And let's say that as it goes to the target, obviously it has to go through several routers. Okay. Let's say it goes through 10 routers. Okay. So by the time this packet reaches here, the TTL is going to be 54. Right? So that's going to be the TTL. Because it gets decremented by every router that it goes past. And if this person is also using the default TTL of 64, okay, the thing that's sent, see, it's not going through any router. So the TTL is going to be 64. Right? So now this person said, that's weird, right? The initial one it supposedly came from the same IP address, but one TTL is 54, and the other TTL is 64. It looks like to me the first one here has been spoofed because it looked like it went through several routers. You see that? Okay, so this is one indication if the target is actually looking for the TTLs. Anybody not see that? Okay, so here's the trick. The 64 is just a recommended. Right? You can change it. So what if, because initially before I did the attack, I know how many hops it takes for me to get to the target, and I said, I see that I have to go through 10 routers before I get through, so I'll just add 10 to it. Okay, so now the TTL is going to be 64. Okay, you see how the trace route can be exploited in this way? Any questions? No questions? Who's going to go through that trouble, right? Now tell me, what is a simple way to stop this thing from happening? How do you stop this from happening? Any ideas? in this scenario that I just told you about. Yeah, Terry. Yeah, let's say this is not even, it doesn't have to be ICMP. I just said it's an attack. So if it's an attack, how can you stop this? I do get your point. ICMPs are used often in attacks. So, if it's an ICMP, yeah, stop the ICMP. I agree with you. But let's say this is not an ICMP. You can still stop this. You can actually stop it at the router. How would you stop this at the router? Okay, so the router is able to see, it has the ACLs. And the ACL, if you do an extended ACL, you can actually look at the source IP address. Look at the source IP address, it's spoofed, right? So it's coming in from an external interface with an internal IP address, or IP address that should belong to the other side. Right? So then you say, that's weird, stop it. Right? Because it's spoofed. Now, this is not going to stop it if the attack is originating inside your network, obviously, because it's not going to go through the router. So if you have an attacker here, that's not going to stop it. But if you have an attacker there on the outside, it should stop it. Okay, are we good? Yes, we are. All right, so let's go ahead and move forward. Okay, so the next one is blind. Oh, it's a non-blind spoofing. Okay, non-blind spoofing. So if what you saw was a blind spoofing, how would you do it so that you're spoofing, but you could still see the effect of the damage? How would you think you could do that? Any ideas? How would you be able to spoof and see the result at the same time? I'm counting. 2001, 2002, 1003. Okay. Let me show you. Okay. So I'm sure there are other ways to do this, but this is just one scenario. Okay. Let's say the attacker is inside. Okay. And you have a switch. Okay. And here is your attacker. Okay. And here is your target. And here is your victim. Okay? So you have the IP of the victim, you have the IP of the target, and you have the IP of the hacker. The step one, once I show you this, you say, oh man, that's so easy, right? So step one, compromise the switch. Make it into a hub. So now you know? Okay? So I've mentioned about, right? Remember the CAM table? Right? Content adjustable memory table. Overflow it, make it into a hub. Okay? So now everything flows out of everywhere. Make sure you have the sniffer on. Okay? And you will send out the attack to the target, right, spoofing the IP address of the victim. The answer comes back to the victim, and it also comes back to you too. But only thing you're doing is you're just sniffing. Okay? You see that? So that would be a non-blind spoofing, wouldn't it? Any questions? Okay. All right. You guys are quiet. You ate too much, right? During lunch? Terry, did you go jogging again? You made meat jump? Went out to lunch and sleepy. I know exactly what you mean. I know, that's why I don't like to do such a technical things in the afternoon, but hey, we got to finish off this domain. So, all right. So the next one is man in the middle. Cooking dinner for kids. Oh, okay, okay. What is meat jun? What's that? What's the jun? Oh, Korean. I love Korean food. Oh, really? Okay, got it. Thanks, Terry. Wanalua? All right, got it. They're good, huh? Are you miss home? Yeah, you oughta come back. I mean, it's not that far away, right? Yeah, I know what you mean. Yeah. I'll definitely remember that. I love Korean food. I was stationed in Korea when I was in the military. I just enjoyed the heck out of the food. All right, so man in the middle. We've seen man in the middle already, right? And but let me actually reiterate that one more time about the man in the middle, so that we're pretty clear about the man in the middle thing. So what you have is basically, let's say you have a doing something with the server B, okay? And let's say the curve is right there, okay? And let's say we already have a session, so a session is going on, and then the takes over the session, right? And so what's happened is that when it takes over the session, B thinks that it is A, right? So B thinks that it's A. Okay, so that's why they start to communicate back and forth. And A goes out of picture, right? So this is session hijacking. Session hijacking. Okay. Then, but if you see this, if B thinks that the hacker is A, and if you do a session hijacking on the other side, something like a session hijacking on the other side, where A starts to talk, right, with the hacker, thinking that the hacker is the server, then you have a man in the middle. Okay, so man in the middle could be, stated as being session hijacking on both sides. Yeah, period. Could you then hijack the man in the middle? Okay, so the hacker. So okay, so so tell me. So you have a second hacker? Is that what you're saying? So the hacker, if you're A, if you A notice the man in the middle. Oh, so A noticed that there's how does A notice that? Yeah, you could, I suppose. How would you notice that you're being? Okay, all right. So you are suspicious, is what you're saying, and then yep. Could you attack? Yeah, of course, you could. I mean, you could technically you could, but would you want to is a question, right? Because so here's a sticky thing. Let's say you are defending in general, and then you notice that you found an attacker, right? Is it okay for you to go after the attacker is a question, I think. It's a more generic question. So, Terry, do you think it's okay for you to go after the attacker? Like attack the attacker? No. Right. So it probably is not a good thing to attack the attacker, but you could definitely observe the attacker if you know that that's the case. So that's, you're almost creating something almost like a honeypot, aren't you? Because you are willingly letting the hacker sort of like trying to compromise you, right? Yeah. And the reason why you don't want to go attack the attacker, I think Carrie, you know this, but for everybody else, is that if somebody's attacking you and you're defending yourself, you have some recourses, like reporting to the police, defending yourself even further. But one of the recourses that you don't want to do is, conversely, attacking the attacker, because then the attacker can actually come back and say, hey, look, this person attacked me. And that has happened before, so that's usually not a best practice. Okay, very good. So this is the difference between man in the middle and the session hijacking. But I've actually started this by showing you how you do, the session exists in the first place. So we started out with session hijacking, and then we went into the man in the middle. But the man in the middle can happen even without this happening. So another one is, right, ICMP redirect is a good one too, right? So that's also man in the middle. Okay. You could do ARP spoofing, right? Remember ARP spoofing that we talked about? That's also man in the middle, right? And you can have a rogue AP. So if you have an AP, let's say, Starbucks or somewhere, here's a real Starbucks AP, and then you have a rogue AP, and people are drinking coffee, happily connecting to your AP, thinking that it's Starbucks AP, and then it goes out to the internet. So right in the middle. Okay, so it's almost like a proxy, isn't it? All right, so that's the man in the middle. Okay, and let's go back to the presentation material. So you have the FINLO and Christmas scanning. This one I'll come back to because I have a different slide set for this one. So let's kind of hold off on that. Let's go for the TCP sequence number attack. We saw that already, right? So we did the session hijacking with it. So that's the example of a TCP sequence number attacks. Okay. The teardrop attack is this. Let me go back. Remember that I showed you on the IP header that you have an offset. You have an offset, and I said that because some routers is going to ask to have this packet broken down into little pieces. Okay? So that happens. Sometimes it happens. So when two routers are talking, okay, and you're sending a packet. I said, and the other side said, for whatever reason, I said, yeah, could you break that down into smaller pieces? Okay, because I can't handle this big piece, right? So let's say you break it down into 3 little pieces and send it on its way. 1, 2, and 3. When it gets to the other side, head to tail, okay, 1, 2, 3. It has to be reassembled that way, okay? So that's where the flag offset, I'm sorry, the fragment offset comes in. So that each of the little piece, the broken down pieces of the packets know exactly how to reassemble themselves. Okay? But the teardrop does this. So by the way, that is in the RFC as well. So whoever is implementing that layer has to be able to implement this in the program. So okay, little pieces come in, I look at the the offset, I put them back together. Right, that's basically what they do. So the question then is, what if you get a whole bunch of little pieces? Whole bunch of little pieces sent to you. Question is, can you, the implementer side, put these little things back together? If there are a whole bunch of them. Bunch of little pieces, okay, like a teardrop. And some implementation cannot handle this because they don't expect these little pieces to come in. They only expect certain pieces to come in, you see? So there is no air condition to catch this thing, so it'll bomb out. That would be the teardrop attack. Okay, that's a teardrop. And so once again, it's an implementation flaw, isn't it? Right? If only the programmer said, you know, if then or else, if then or else, and make sure that they cover all the bases so that if something unusual happens, that it fails gracefully. You know, not just bombing out. That it's just a flaw in programming. The next one, I know you don't see it, but the next one is called the overlapping fragmentation attack. Okay, overlapping fragment attack. So what happens in this case is very similar to what you just saw, the teardrop. Okay, but it's not the little thing that comes in now. So now the fragment comes in 3 pieces, but the fragment offset overlaps. Right? So there are pieces where the numbers don't go head to tail, head to tail. So you notice how they overlap. Okay? So when it goes to the other side, the question is, this is going to cause an error, obviously, right? Because it doesn't fit, right? They'll try to fit it, but then it kind of starts out here somewhere, and then the next one kind of starts up here somewhere. So this is an error condition, okay? And the question is, can the receiving side handle this type of error? And if it can't, it may bomb out. Once again, it's not catching the error properly and failing gracefully. Alrighty, so those are the overlapping fragment attack. Okay, we're just talking about network attacks here. Okay. All right, so let's go back to the presentation material. Get another refill of the cold coconut water. Coconut water is so good for you, so they say. It does have some calories, but it's pretty minimal. And they're natural sugar too. Comes from the coconut. Okay. The next one is source routing exploitation. Alright, so who knows what source routing is? What is source routing? CCNA, CCNP. What is what is source routing? Oh, come on. Source routing. No? Very. That's right. So you specify which route a packet is going to go through. And who specifies that, Terry? Because normally it is done, by the routers, right? Using routers will decide what is the best way to go depending upon the routing protocol that they use. I think somebody else is telling the packet to go through a particular route. But if you put the weights, you're actually changing the router. And source routing isn't about changing the router. Okay? All right, so I'm going to switch to the whiteboard so I could show what happens here. Source routing is a perfectly fine option for, it used to be used for a troubleshooting. So Terry had it right, partly, but the part about changing the weight wasn't the one that was quite it, okay? So it's a person. It's actually the sender. The source is the sender. Okay, and here's what happens. So let's say, here you are. Okay, and this thing goes into the cloud, and what you want to do is you want to connect to something. So let's say that you're A, and here's B. Okay, and if you want the packet to go from A to B, okay, you want it to send it to B, right? I want to go to B. If you leave it up this way, normally, the routers are going to look at their routing tables and make the best, least expensive route. Just let's say you have these two routes, okay? And let's say the OSPF takes you through this route, okay? But what you can do, well, let me change this just a little bit. So just a little bit, so that maybe it'll go this way too. Okay, you can have these kinds of routes. This person right here, this person can say, you know what? I want you to go. I want you to go. Ignore what the router said. Go this way, okay, and then from here take whatever's the best route. So then they'll say, something like, okay, so let me go through this way, or let me go through this way. You see? So that's specifying partial route. So you say, I want you to take this, this, and this. It wouldn't go that way if you just leave it up to a routing table, or routing tables, or the routing protocol. But you're forcing it to go through a different route. So you can specify, the person can specify partial route or the entire route. So you can actually say, nope, what I want you to do is I want you to go through, this one, this one, this one, this one, and then this one. Go through that way. Go that way. Okay? And notice how that could be a very, handy way of troubleshooting. You say, look, A is not getting to B. If somebody says, A is not getting to B, well, I wonder what's happening. Well, let's see. Let's see if it can actually go through the other route. And if it does go the other route, let's say it goes to the bottom route, and says, oh, actually A can talk to B if you go to the bottom route, but if you just leave it up to the routing table, it tries to go to a different route and it doesn't get to B. So maybe there's something happening, something wrong with the router settings in one of these routers. Right? You see how that could be a troubleshooting tool. Okay? So that's basically what source routing is. But what's the problem with this? What is the problem with it? What could possibly be the trouble with this then? You don't see any problems with it? Okay, so remember, as a hacker, you may say, look, I don't want to go here because I think they may be doing a lot of monitoring. I don't want to be known. I don't want to go through that route. Okay. So, for example, and I'm just making this up. Well, I'm making up some of it. Okay. But in fact, in one of the books that I read, I think it's the book that I recommended to you, the dark web. The 80%, whopping 80% of the internet traffic goes through the United States. And that 80% of the traffic goes through one of these main exchanges, internet exchanges. And those exchanges, I think there's like 4 or something, main exchanges in the United States. So if somebody tries to monitor, well, something happened to Lisa. Hey, Lisa. Yeah, Lisa, can you hear me now? What happened? Technical issues. Okay, all right, got it. All right. So let's say, you say, that could be like an NSA thing. I'm just, you know, I'm just putting it there. Okay, but they actually did do that long time ago. I'm not sure if they're still doing that. They said, I don't want that to happen, so I'm going to go this direction. See that? Right. So there you go. So these days, source routing is turned off by default. So even if somebody tried to say, I don't want you to go that way, I want you to go this way, router's going to ignore it and say, nope, sorry, source routing, you know, off by default. You will go where I tell you will go. Okay, is it coming back to you, Terry? Yeah, slowly. Okay. All right. So let's go back. Yeah, I'm going to be teaching CCNA pretty soon, so I better come back and start remembering these things. Okay, so let's go with a Smurf and a Fraggle attack. And no, I don't know why these things are named this way, but let's see. Maybe somebody knows. So it'll be interesting where the name came from. But let's go for attack. So the Smurf attack works this way. And you know, not only I'm hoping that as you're listening to this, right? Not only are you kind of getting an idea of what these attacks are, you know, getting just a basic understanding of how these attacks happen in general, right? It's all about there's always has to be a vulnerability. There's got to be a weakness, okay? And we're just picking and choosing and showing you stuff that people use because they found a weakness. Okay? All right, so let's say I'm going to draw it a little bit differently here. Let's say you have a victim, and then you have all the happy workstations that are in that same segment, the broadcast segment. Okay, so broadcast domain. And let's say that you have here is trying to do something really bad. So this person does a ping. Ping. Okay, does a ping. And spoofs the IP address to the victim. So if that normally happens, reply back to the victim. But that's no fun, right? That's no fun. So what happens here is that this ping is what's called a broadcast ping. So it's going to go to every single workstation on that segment. And the hope is that you have a whole bunch of these things so that they all come back to that. And of course, this ping will keep on flowing, and these pings will keep on going back. Notice how the victim will be inundated with this thing. Okay, so the issue, of course, is that ping is really it's not supposed to be a broadcast thing. It's supposed to be like, you know, unicast ping, you know, just one ping and come back, one ping and come back. You don't say all the segments ping me back. But this is once again a flaw, and there you go. This is a Smurf attack. Smurf. Okay. Then you have a party pooper like Terry that says, well, I'm not going to let ICMP go through my firewall. So maybe this thing just stops the ICMP. Stop ICMP. Okay, so everything stops right there because pings do this kind of stuff. Okay, but then of course it's always a cat and mouse game. So the hacker says, no problem, Terry. We're going to do something called the TCP ping, UDP ping. So they're not really pings, okay? But they'll do something similar, like this. But another problem, another way you can stop this is, once again, this is spoofing an IP address of V. So the victim is on this side. So you could say, well, you know, the internal IP address does not belong, it does not come in from the external side, so you don't get to do this. So you can stop that right there with that filter, which nowadays is a normal thing to do, absolutely a normal thing to do. Yeah, Terry. Oh, is that right? World of Warcraft. Wow. And Smurf is one of the names? Oh, I see. It's called smurfing. Oh, by using a different name. So it's about it's about spoofing then. So it's another name for something like spoofing. I see. So where do you think Fraggle comes from? No, it's not. It's not one of those. So the TCP ping and UDP ping is called Fraggle attack. Okay. By the way, do you play the World of Warcraft? I just heard that that's like a pretty wild but pretty involved game. Yeah, but I still hear that it's pretty big. But yeah, wow. Okay, good to go. So then let's go ahead and let's see if there are no questions on this one. Let me just save that one. Okay, and move back. Program. Okay, so we did the Smurf and Fraggle. We are still going to cover the Fin, the Null, and the Christmas scan. Oh my god. I'm not sure if you know what a bully stick is, but bully stick is a something I gave to my dog. It was at least feet and a half. It was a huge bully stick. He just ate the whole thing in an hour. That's amazing. That was $20. He ate it up and he ate it up $20 in an hour. Man, there's something nutty about this dog. So here it goes. So here's DDoS. Okay, so DOS we know right now is service, and let's just take a look at DOS. Right. So DOS is any type of attack that will prevent you from accessing the system in the way that you designed it. Okay. So of course you can do a DOS by overfilling the network so that other people can't get into it. But you can also do a DOS by walking right up to the server and spilling coffee on it. Right. So DOS means it could happen in any way, but the BDOS is a little bit different, right? So distributed denial service is mostly we're talking about something like botnets, that you have the attack source that are highly distributed and in high numbers. So that, and when they do a concerted attack on one target, right, it's very overwhelming. So that's what a DDoS is, right? Usually bots are used for that, right? Botnets. Okay. Right, the SIM flooding. SIM flooding takes an advantage of the three-way handshake. Okay, once again, it's not a vulnerable. It is a weakness in a way, but So let's take a look at how this thing works. So SIM flood. So the SIM flood. Okay, so you have a client, and then you have the target. Okay, so well actually. I want to actually make this just a hacker. So here's a hacker, right? And then you have a target server. Okay? And what the attacker would do is send a SYN. Right? But the source IP is spoofed. So IP is spoofed into a black hole. So it's out here someplace. Well, let me make it black. So it's a black hole. So nobody's going to answer it. Okay? So if the service is open, if the port is open, it wants to send a SYN. Okay? But it's not going to receive anything back because there's nobody there. Okay? But the thing is, it doesn't know that. right? So it's going to wait a little bit. It's going to wait. It says, it's almost like saying, somebody calling you and you answer hello, and there's nobody's talking, right? So you kind of wait and say hello, hello, right? That's basically what the target is doing. And while the target is doing that, this thing's going to send another SIM, and another SIM, and another SIM, and the server is going to keep on sending it back, sending it back, sending it back, waiting, waiting, waiting. Maybe this will time out. But the thing is, this will keep on sending stuff back. Notice how there's SIM is flooding, right? And eventually, the target is all the target's memory is going to be used up. Well, there's the set of pool of memory that is set aside just for accepting these new connections, and that's going to be used up. Okay, and when it is used up, okay, and while it keeps on going, when you have a real user that wants to connect, it can't, because the target is just too occupied, right, with the SIM flood. Okay, so it's basically a denial of service to that person. Can't access the server. Alrighty? Okay, so getting back to this, right? Spoofing, we've already done spoofing, right? Session hijacking, we've already done session hijacking, right? IP spoofing, yes. Man in the middle, yes, right? So what's remaining is my showing you the presentation for the thin, null, and Christmas scanning. And what you need to know about the thin, null, and Christmas scanning is that it's not really an attack on its own. It is a scanning technique. Actually, these are stealthy scanning techniques, so that whoever's watching out for scanning activities will miss it. Nowadays they won't miss it because they understand these things happen. But these things are there. If people are not looking, yeah, it may work. Okay, so let me get that out. So hang on here. We open up a new tab. And okay, here we go. Okay. Scan network. This is my CEA slide. I keep CEA as well. All right. Scanning is just a part of the attack. I'm just going to skip through stuff that we don't need. Scanning methodology. Don't go through this thing. I'm almost there. Okay, so the scanning techniques. So there's something called the TCP Connect Full Open Scan. I'll show you how that works, and then we'll do a stealth scan. Okay, and within that stealth scan, you see there is the thin scan, Christmas scan, thin scan, and null scan. Right. So those are all the stuff that you need to know. So let me go ahead and go there. Okay. So initially, if you are doing scanning, right, so I'm going to cover this one more time in the testing and assessment phase on the domain. But when people do scanning, there are three different types of scans. One is called the ping scan, the other one is called the port scan, and the other one is called the vulnerability scan. And it happens in that order. Okay? The ping scan is mainly to find out, you do ICMP ping on a segment of the network that you want to attack and see how many hosts you can actually touch. That is, you do a ping and whether it comes back or not. Okay, you're looking for that. So then, let's say out of maybe 20 servers out there, you get response back from 5. As a minimum, okay, unless there are honeypots, that you can actually communicate with these 5 servers. Then you say, okay, for these 5 servers, what services are available? You're looking for open ports because those are possible vulnerability points. So you do what's called a port scan. So, and the fin scans and null scans and all that is a type of port scan. So you're scanning all the ports, from 0 to 65,535, both on TCP and UDP ports, and making lists of all the ports that are open. Okay, and the question then is, how do you know if the port is open or not? Okay, and that's basically what the scanning section explains. Just to be complete, after you have all the ports, then you will interrogate each of the ports by sending messages to each of those ports to figure out for it to reply back to you with, let's say, like a version number and the actual the server that's running, right? So that's basically what you're looking for. And once you know the version number of, let's say, IIS or Apache, you can always go to National Vulnerability Database or something like it to find out if there are any the vulnerabilities that you can take advantage of. So that would be the vulnerability scan. Right. So now, if you are doing these scans, and if you are not worried about alerting your IT security staff, okay, or if you're a consultant and you're doing the scan and you ask the customer, hey, do you guys really want me to just do the scan, or do you want me to test your IT security staff as well? If the customer says, no, don't worry about it, we'll let the IT security folks know that you're scanning, so they won't stop you from doing it, then in that case you don't have to be stealthy, do you? Because there's an agreement, okay, that you can make all kinds of noise, because what you want to do is you're just trying to come up with all the ports. But if the customer says, yeah, it would be nice if we could test IT security staff too, to see if they can actually catch you doing these scans, well, in that case, then you do stealthy scan. You do other things too, but one of the things, of course, you do is you do a stealthy scan. In the case that you don't have to be stealthy, TCP Connect full open scan is the easiest thing to do. So, for example, this is the basics. So let me actually show you. Okay, so yeah. We'll get the command prompt out and show you the command prompt. Okay. Alright, so let's say I have a friend who's working in the in training industry, and Netcat. She's in Guam, and I do 480, so I know she has a website there. So if I do that, I'll say something like get. Okay. So I just pretended to be like a browser, and I sent this information in, and it came back, right? So it says, so this is a full connect scan, but I connected because the HTTP came back to me. Okay? So you see there, what I'm looking for is, look, it's a bad request, that's fine, but what I'm looking for is, see, where's the server, right? So it's NGINX 1.10.0, so that's a version number, okay? So now I can take that information and stick it into the vulnerability database and see if there's any type of vulnerability there. Okay? But what have I done here? Because I connected, I did a full connect, that is, I did a three-way handshake, and then I did a four-way handshake to tear down the connection. I'm logged, right? So she's logged me, I'm sure, in her web server, definitely logged me. If she has an IDS, they probably log me as well, because I made a full connection. See that? Okay. So, this is, and by the way, this is part of what you do with the vulnerability scan as well. Okay. So anyway, then let's go back then to the presentation material. Okay. So what just happened, right, when I did the net scan? Well, what I did was, if you take a look at that part right there, the yellow part, okay, the target's port is, 80 is open, that is, web server is running, if I were to do a SYN to port 80, it's going to come back with SYN ACK. And then I would send an ACK back, right? That completes the three-way handshake. But because all I wanted to know as an attacker is whether if I'm going to get the SYN ACK back or not, then I said, well, yeah, I just want to do the three-way handshake, but look, I don't have anything, I don't want to do anything else with you, so let's just go ahead and reset this, session. So you set a reset. If you then do a reset, well, target's going to expect you to, attacker, to send something else, like, get me a page or something like that. So you don't want that kind of problem because, look, you actually have to do a scan on 65,535 ports. You don't have time. So you want to go ahead and reset, move on to the next port. You ping 81, reset, port 82, reset, port 83, reset, on and on and on. And if the port is open, you're going to get a SYN ACK back. If the port is closed, you're going to get a reset back from the target. And the scanner is looking for, am I getting a SYN ACK back or am I getting a reset back? And then you make a list and say, okay, this one's open, this one's closed, this one's open, this one's open, this one's closed. Okay, so that would be the full connect scan. Now you want to do, you're basically looking for all, the end result is you want to know if the port is open or not. So now the stealthy scan, the one that you need to know. This one is called a half-open scan. So the half-open scan is, you do the SYN on port 80, it comes back with SYN ACK, but you don't return an ACK. You just send a reset. Now, if you don't send a reset, this is one of the side of the SYN flooding, right? But in fact, this is not really a SYN flood because you're not spoofing the IP address. Okay? So just to make sure that the Sheila is not going to, you're not going to create a DOS situation for Sheila, you do set a reset. But because you have not created you have not completed the session, the three-way handshake, hopefully this will not be logged. And if the port is closed, same thing, you're going to get a reset back. Okay? So now let's go to the other ones. Christmas scan. So the Christmas scan, you are sending a packet with a port. So you're sending a thin urge push to port 80, let's say. Okay? Now, if port 80 is open, right? If port 80 is open, port 80 looks at it and says, what is this thing? You haven't created a session. You're supposed to send me a SYN first. Okay? But it didn't. The only thing it got was thin urgent push. So it doesn't make sense. So under the RFC, the server doesn't have to respond to this. So it doesn't. Okay? But if the port is closed, it's going to do a reset. Okay? So the scanner knows that when you do a thin urgent push, if there's no response, then the port is open. If you get a reset, the port is closed. Okay? Fin scan. Same thing. I'm hoping you've seen the pattern. Okay? So the attacker sends a fin. Well, if the port is open, server says, look, you can only send a fin if you already have a session. We don't have a session. So fin does not make sense to me. I'm not going to respond. If the port is open. If the port is closed, it's going to send a reset ACK. There we go. Okay? And there's the null scan. Now this time it's a TCP packet with no flag set. Once again, server said, look, we don't have a session. Please send me SYN and ACK first. Okay? So no response. If the port is closed, reset ACK. Okay, and in all these cases, because the session is not being created, we're hoping, as an attacker, is that this is stealthy. That is, nobody's looking for it. Okay. Any questions on these? Any questions? No? Very good then. If that's the case, we are done. That's the shaka sign. Yeah, so we're done on the network side. So let us take a 10-minute break, okay? And when we come back, we're going to move on to the next domain. All right. Thank you very much. I'll see you back in 10 minutes.